All right, how you guys doing? How many of you are not happy to see me today after the exam? I will get a formal poll to see how you felt about the exam. I didn't prepare it yet this time, but just show of hands, you felt like it was, let's say, harder than you expected. Felt like it was challenging, but maybe about right. Anybody you care to admit that you felt like it was easy? All right. So I've only begun to grade it. I've got about a quarter of the way through so far. I will be making more progress on it this week. I don't know if I'll have it to you by Thursday, but I will spend at least most of a class period with you on it when I do, to go through the solutions, pass them back, go through the solutions, and get a better poll for how you felt about it. You might feel a little better once you see, okay, if you get the problem wrong, I'm not taking full credit off unless you basically didn't try or didn't show me anything that you learned. So I'm generally like, and I apologize, I meant to give you a little warning about this first. Somebody even said coming into the exam, oh, what is it going to be like? Is this multiple choice? And usually students ask me for that, and so I explained that before the exam. So I apologize that I should give that information to you, but there you have it. That's what it was. But I will say I do give partial credit. I'm really aiming to test you on and grade you on what you learned and what I can see that you've learned, not on like perfection there, getting everything exactly right. Now, when you get it right, it makes it easier for me to grade, so I appreciate that. But you will be getting partial credit, pretty much guaranteed on that. Okay, so maybe Thursday. If not, then pretty for sure I'll have it back to you a week from today. All right, any big questions or concerns on that? All right, so hopefully that'll be possibly Thursday. Today we'll begin talking about filtration, and I think it's a little bit shorter. I've got a couple videos to share. Essentially, there's two types of filtration that we might deal with. There are more than that in reality. Maybe we could talk about biofiltration or something that combines biological activity, but for the sake of in our drinking water treatment and for the sake of this class, what we're going to basically talk about is two forms of filtration, primarily for particulate removal. So after the sedimentation, we use gravity to do what we can, and we do that coagulation, flocculation. Then we would typically do sedimentation again to use gravity now that we made larger particles. After that, we have a choice between using what we call granular filtration, which is what we'll talk about today and a bit next time, or membrane filtration. The difference here is when we use granular filtration, it's acting a lot like soil in a sense. So we'll have a bed of sand or something like it, and that's our media, granular media. We could pack this into a column and pressurize it and use it as a pressurized column. That'll look a lot like an adsorption process if you're familiar with anything like that. You've probably seen these at swimming pools with a little cartridge thing. It's like about that size, something like that, and it has pipes going in the top and stuff. That's essentially a sand filter or maybe a carbon filter. And it's going to be packed with granules, and water will be pushed into it and through it, and it'll have some cleaning. And then eventually you'll have to backwash it and get rid of all the particles. Now, in water treatment, we sometimes we'll pack it into a column like that for something like a pool. For larger systems, a lot of times we'll just simply let the water accumulate on top of this bed of sand and just let gravity drive it through. Of course, we have to pump the water up, so we're using some energy, but we're pushing the water through, and so the flow would be water's coming in and then traveling through and being collected out the bottom under normal operation. Now, these filters have to be backwashed with some frequency. So a lot of the design challenge on them is how do we know we have enough filters to handle routine maintenance? So if they're going to be backwashed every 2 days or something, then how do we know we have enough filter area to accommodate. So the math for this part of the class is going to be rather straightforward, but it introduces a nice concept of flux of water across that membrane, or excuse me, across that filter, which is the same type of concept we will use for membrane filtration, which we'll come to later, but just as a quick little thing, a membrane filter operates like a screen, like a mesh, where you have a particle in water and it's traveling and it gets stuck as the water travels through and cannot make it across. That's a little different than sand. In the sand case, we're actually allowing the particle to stick to the edges of the pores or stick to each other and accumulate and grow into larger particles that then get stuck. Most of the granular filtration is not actually size exclusion because the pore sizes are relatively large, but it allows for a lot of area for these particles to stick to the walls, to the sand, to whatever else. And that's very likely because we've destabilized them. So part of that coagulation flocculation, that coagulant destabilizes the particles, so it helps with sedimentation, but even after then, once these particles are still sticky, but a few of them make it through without gathering into larger particles, now they're happy to stick to our sand. So it kind of does a dual action for us. So it's very common then to use sedimentation, coagulation, flocculation, sedimentation again, and then granular filtration. It's very routine because it just works so well together, and most of that's using gravity and a bit of chemicals. Okay, so a couple common examples. We can think of actually coffee grounds. So as you pour water through coffee grounds, the grounds are kind of like a media bed, except they're going to release stuff, right? You want the stuff to soak out of the coffee grinds. But they could potentially filter something if you had, let's say, some leaves in your water and you poured it onto some coffee grounds. Well, the leaves are going to get caught, right? So that's the granular filtration, sort of. The coffee filter would be like a membrane because it's physically excluding stuff. That analogy is not perfect, but you've seen Brita filters. It's a better example of this granular filtration. It's allowing space for chemicals to adsorb onto the carbon that's there. Soil's another example. And the coffee filter is a little bit more like the membrane because it's excluding particles based on their size. You can get some really fine particulate matter to go through, perhaps. Or a screen porch trying to keep mosquitoes out. Okay, so today we're going to talk about the granular filtration then. I mentioned it's usually not size exclusion. So if we think about what the media might look like, it could look something like this, where we have a particle here. Size exclusion, yeah, it can happen if you have a large particle. Usually those large particles were removed from sedimentation, but if they're there, it could get caught and separated. More often, you're going to have an assortment of different properties or different processes that we could talk about. You might have flocculation within the pores, particles meeting each other. You might have direct sedimentation. We talked about the big sedimentation basin. The particle has to travel some distance before it hits the ground and then it's separated. Well, there's very small different distances to settle inside these pores. So if it just settles a little bit along its way and makes contact with the surface and sticks, then it's sedimented just inside the pores of the granular media. You could have interception, where it's not exactly sedimentation, but as the water is moving along the pores, say here's a granule, a particle along the way ends up hitting the edge because it doesn't move out of the way in time, kind of thing. It's not carried, the fluid just kind of ends up bashing it into the side of the pore wall there. And so you could have interception like that, or impaction, where kind of the same deal, where it's just the water moves and the particle slams into the granule. Whatever the case, there's a lot of different mechanisms we could think about that are going to stick. That's the point. And it's going to be not like a permanent sticking. If we were to keep pouring water through it forever, then eventually we're going to have some of this make its way out, which is part of why we have to backwash and clean it out. And especially if we had dirty water, eventually that dirty water, some of the particles will start escaping. So we might consider the fact that as we operate something like this over time, we will eventually have particles escaping. It's a little bit like using Velcro, right? Adsorption processes are a little bit that way. If you have some Velcro and you shove a lot of dust and fuzz on it, eventually all the sticky spots will be filled until you remove all the dust and fuzz and stuff. Then it could be sticky again or grabby. So that's going to be the same type of concept that's happening in granular filtration. Now, here's a couple examples. Normally, I have this pilot system in my lab. That's somebody's borrowing it to use it for some test stuff, and a consulting company's borrowing it right now. But if you're very interested, I could probably hook you up with a visit to go see it wherever it is. It's not too crazy of a system. This one's 3 columns packed with some granular media. You can see them, in practice might look something like this. We'll look at a few examples as well in a moment that are the bed variety. So I mentioned these would be the column ones. The reason you might want a column, you could probably push it a little higher pressure, meaning higher flow rate, but there are some limitations. If you put too much pressure, eventually the sand is just going to give away and fissure, and then you're not getting any filtration. It's just channeling through it the most direct, shortest path possible. So you have to operate these in a careful manner, not to prevent any short circuiting or anything like that. But a confinement like that does help. So more often than not, it's going to be a whole lot of sand or small granules in a very large bed. And so you see here about maybe a cubic meter or more of media being added into this bed, and you can see a worker there for perspective. These are very large systems and going to be packed with a whole lot of media. So considering how well the media functions, does it ever need to be replaced? How sticky is it, given the type of particles we have in the water, things like that. Operators might have a few choices on, okay, how do we design this? What are the cost benefits? And they're going to need a lot of that material. And ideally, you don't ever replace it. And so in operation, you're doing so, and you're doing your backwashing in a way that you shouldn't be losing any of this sand. You shouldn't be flushing it so fast that your sand is escaping with the particles. A few more examples of what it might look like. I have no idea where this is, but it looks like a nice place. You can see these are just large beds, and they just have water piled up, and the water is, it looks pretty still, and perhaps that would be a sedimentation basin, but I think these are multiple granular filtration beds where water is seeping down through continuously, and eventually they would stop that and backwash it. We'll give some examples of that. Okay, so when did we first start using granular filtration? Well, as soon as we were using groundwater is the simple example. But really, in terms of intentional treatment, I think the earliest sand filters were actually what we would call today slow sand filters, or maybe bio sand filters, meaning that we give the water a lot of time with a high surface area material. There's going to be some of that filtration, but because we didn't have the sophistication 150 years ago to backwash and pump stuff, all of that, we would let bacteria eat all the particles. And so there'd just be continuous bacterial activity as we're letting water go through. And that's not a great thing because we've then got a lot of bacteria around, but hopefully it's at least going to remove a lot of the particles, and the bacteria that are growing in the sand are not so likely to be the same bacteria that would give us an infection. So it'd be a little benefit, better than just taking untreated water. So that's even today sometimes used for biological treatment, but not really something we use for drinking water anymore. So that's kind of the history. Typically what we use, I've mentioned sand. There's you could also think of anthracite, kind of mineral stuff, some combination, or granular activated carbon. And a lot of times there'll be some mixture. Some scenarios where you're doing something a little more specialized, like the sand filters I showed you, that pilot system that I had in my lab, that actually is loaded with stuff for iron removal, and that's a green sand plus. So it's got a special coating to these anthracite particles that allows for a bit of chemistry to stick to help iron oxidize and arsenic and stick to those columns for removal. It's a little more advanced of a process, not just for the particles, but for some dissolved stuff. Okay, but generally it's pretty simple. You have to have a type of sand. You want them to be pretty much uniform in size, so you have a pretty uniform pore size. Maybe you have 2 layers. If there's a different density, then when you backwash, they will resegregate into their layers. So that's kind of common to have some mixture, maybe 50-50 ratio or something. And it's self-sorting, so you know, if it did matter, you don't have to worry too much about that. All right, so there's a few terms we're going to use in describing our granular filtration. When we talk about the operation, when do we start, when do we stop? And so I need to introduce a few terms to you that we're just going to use for this topic. First would be the filter ripening. If you've ever used a Brita filter, how many of you have used like a water filter like that? You ever put in a new cartridge and there's like black stuff coming out? Yeah, so that's the ripening stage. It's got some loose junk in it. Maybe it's a brand new filter. Maybe it had just been backwashed, so it has a little bit of the junk particles in it. So that wouldn't be true for the Brita filter, right? Because you're not going to backwash and reuse that one. But during operation, you can imagine if all the particles were just jostled about and backwashed, there might be some junk still hanging out. You have to get rid of that before you're ready to use the water. After maybe 20 minutes of operation, or in the case of the Brita filter, maybe like 5 jugs full or something, you see that most of those, gross looking particles are gone, and you're like, okay, I guess it's safe now, right? It turns out those particles are pretty safe. It's just, you don't want to drink them, right? So in that case, that's the ripening stage. You have to flush out all of that stuff. It's kind of a warm-up or, acclimation step. This is dirty water coming out at first. So we don't want to use that. So that water goes to waste. That's not something we're going to use for our drinking supply. Then there's backwashing. That's kind of obvious, self-evident. We're going to use treated water because we're trying to clean these filters. So we're going to use treated water, which means we are consuming some of the water we just produced and flush it in reverse. We might also do an air purge. We'll see an example of that. And that's going to clean and regenerate the filter. Now, ideally, we can do this ad nauseum, as many cycles as we want. And that is generally the case. That water, of course, is wasted and is going to be routed to a wastewater treatment of some sort. Maybe the treatment facility has a small wastewater system on site as well, or maybe it ships it off to the local sewer system and they're going to deal with that as they will. Regardless, we have now 2 cases where we're taking water that would have been good and either directly wasting it or just not keeping it, right? So this is also a source of water loss in some sense. So as we consider to do a calculation, we have to accommodate for the fact that not all of the water that we're taking into the plant is actually going to be used. So we have some efficiency factor there for the backwashing and that rinsing or ripening step. It's another way to say it is rinsing, so I'll probably use those terms interchangeably. Okay, next would be head loss. And this is referring to the hydraulic head or pressure of water on top of the filter. So as we're pouring more and more water onto the filter, eventually it starts getting a bit clogged and it takes a little more force to push water through. The convenient thing is we can just simply operate in a way where we add a certain flux or certain flow rate of water, and the gravity will naturally adapt for and account for the pressure required to push the water through. Because if we're giving, I don't know, 1 cubic meter per second of water, then that means the water level might rise a little bit to force 1 cubic meter of water through. And so we'll achieve some sort of a steady state, and that'll just adjust a little bit as the pressure requirement increases. So that'll give us a way to operate maybe with a couple meters worth of distance of hydraulic head that can accumulate on top of the filter to automatically, so to speak, account for the pressure needed. Which is very convenient, but eventually we could get to a point where we don't have any more room or we have too much pressure. So we have to, in some ways, account for or watch out for the head loss. Maybe this is a way to decide, okay, it's time to wash the filter, right? So it's one of the possibilities. Okay, the other term here that's very important is turbidity. Do you guys know what turbidity is? Any of you? Okay, turbidity is essentially the cloudiness of water. So if you think of mud, you'd say that, oh, that's muddy water, or it's murky water. What you're really saying is light's not traveling very far through it, and not just that, the reason the light's not traveling far through it is because there's particles scattering light. So if you think of visibility through air or into water, any of you travel out into the ocean, like way beyond the Mississippi effect area, just way out. So if you travel far away, like into the Gulf or into the Atlantic somewhere, if you get away from all the sediment that's in the water, you'll end up finding very clear water. Certain locations that don't have much sediment, even close to the shore, can be like that. Certain natural springs, not a lot in Louisiana because we have mostly sediment here, right? Years and years and years of sediment from the Mississippi everywhere. So in some places, you'll find water that you could see 20, 30 feet through, right? It's nice, clear, looks like stuff you might want to drink. Other times, you'll find water that is very cloudy or murky, and that's turbidity. So turbidity is measurement of that light scattering caused by particles. Another good example would be if you take tea and it's been filtered nicely, you should be able to see through it even though it's colored. That's different than having a brown muddy color that's muddy, meaning you can't see through it like you can see through tea, right? You could look at rivers in the same way. If you have a very low turbidity river, but it might have a brown stain, it would look brown, but you can see clearly through it. That's possible. Right, so that's the concept you can find. So milk is very turbid. You can't see very far through it. There's particles scattering that light. Okay, so turbidity then is a measure of particles in the water. It's like a concentration kind of a deal. It has this funny unit that we call nephelometric turbidity units. Good example here of turbid water. So we have clear and increasingly high turbidity. Again, it's basically saying murky. Okay, it's just the technical term for that. A way to measure it is to measure how far you can distinguish this, like a black and white edge, as we see on this little Shecky disc thing. How far through the water is your distance, is your visibility. So people will literally go out and measure that with a rope and see, okay, at this point, I can no longer really distinguish what's the white part of that and what's the black part of that. And that's a simple way to see what's your visibility, and then use a, whatever metric to say, okay, that's this number of turbidity units. So it's a little bit arbitrary seeming in terms of how we define the units, but we can quantify it with the amount of light scattered in that manner. So it might look something like that. And as you see, you can imagine if you drop that further in from at that point, it's probably going to get to a point where you can see that it's there, but you can no longer see exactly where the edges are of the black and white spots. Okay, so then probably the most important variable for our granular filtration operation is what frequency do we backwash? When do we backwash? How long is it going to take? How much water are we going to use? What's the impact of that backwashing? That's going to drive a lot of our design for a granular filter. So In order to determine when we backwash, there's kind of three methods, and usually we'd use at least two of these. One would be head loss. The next would be just a simple time limit. And the last would be monitoring that turbidity. Because if we have turbidity coming out of the filter, we know that our particles are starting to escape. So that's going to tell us at some point we need to wash because the filter is kind of full of particles and they're starting to make their way through. So turbidity limits then are usually a kind of safeguard. We typically will have online turbidity monitoring if things are going well, and that will tell us if there's some problem with the filter. Maybe something else happens wrong and something gets out of place or is not working properly and a filter malfunctions. We'll see that turbidity coming out, and that will be a way to tell us, oh, okay, we need to stop that filter operation right now and backwash or maintenance it accordingly. There is a reading assignment I'm going to post to Moodle. It might be there already, and I'll have a associated quiz later on in a week or two about a big cryptosporidium outbreak. Cryptosporidium is a pathogen. We might call it a parasite because it's like a slightly larger cell than a bacteria. It's like a eukaryotic cell, harder to kill. It's like the Giardia and Cryptosporidium are the common hiker's diarrhea things you hear about. So anyway, it's a pathogen, and there was a very big outbreak in Milwaukee in the 90s, early 90s, and affected quite a lot of people, and it had a lot to do, or one component of it was their turbidity monitoring was not going on. And they were using granular filtration, they weren't operating it well, and they didn't realize they had a lot of particles escaping, and essentially they concentrated the pathogen and sent it out into the distribution system by mistake. So that was not good. So I'll be posting that probably later today. So this was a big part of that outbreak. Okay, so if we monitor the turbidity over time during one cycle, well, first of all, we could imagine one cycle, let's say in hours. At some point, we're going to stop and do backwashing. For a long time, we're going to be filtering and producing water. We'll call this a production step. And then at the beginning of our cycle, if this is time 0 for one cycle, this would be that rinsing or ripening stage. So if we monitor the turbidity over this period of time throughout rinsing and then production, we probably, and let's set a limit too. Let's say we have a turbidity limit here. Pretend that's a straight line. And we'll monitor the amount of particles, essentially, the turbidity coming out of the filter. Well, during the ripening phase, we're usually over the limit, right? So for the first few minutes, maybe first half hour, and then should drop, we'll be over the limit. And then by the time we start production, we should be back under the limit. And then it should be pretty stable for a long time, and then slowly starting to rise. And as soon as we cross, we should probably stop and backwash. So if our typical time was to start backwashing over here, maybe we need to shift it earlier the way I drew it, right? So at this point, we've reached our limit, and that would be a signal to do a cutoff, right? To stop filtration. Now, normally we'd probably design it so that our turbidity limit doesn't normally happen before our time limit if we're going to do a time limit. So a lot of the cases we'll talk about, we're just going to set a time limit and describe it that way. So that would be kind of the implementation of a turbidity monitoring and limiting type of system. Now the operational time, these can range anywhere from maybe 24 hours to 3 or 4 days, maybe 100 hours before you need a backwash. Really depends on the system and how dirty the water is. Typically, you'll have at least a turbidity limit, and then either the head loss limit or a time limit. Sometimes you might have the time limit and then monitor head loss and turbidity to do it that way. Okay, so let's do the same consideration for head loss. Take a look at what that might look like. And I'm also going to just be a little more clear here about one cycle. So if this is our start, we would have some time frame for the rinsing and ripening. That might be something like 15 minutes. Then we have production. I'll say anywhere between 24, I don't know, to maybe 96 hours. Those are not hard and fast numbers, you know, but that's a typical range. And then we'd have backwashing at that point. If we add in an air purge moment, we're going to drain it and then pump some air through it to jostle the sand really well. That would probably happen first. So we might account for air purge optionally. Now, an air purge, we're not using any water. So when we calculate the water usage, that's time we're taking that's not producing water, but at least we're not consuming water. So as we think about putting all the pieces together, it's not super complicated when we do, we'll notice that we're going to need a total cycle time, and we'll need to know how much water we're producing over that cycle time, and we calculate it according to the time we're producing, the amount we're not producing, and the amount of water, we are taking away from what we produced, and averaging. So we might have a production rate, but it's only 95% of the time of the total cycle is actually producing, right? So we just have to account for all the pieces like that. And then finally, we'd have a backwash. So air purge, this would be like 5 minutes. And a backwash would be something like 15 minutes. Okay, so if that's our total cycle, typical, we could then say total cycle time, or TC. So that time frame might be like 100 hours or 97 hours, something like that, or maybe 25 hours. Maybe we just call it exactly 24 hours and our production time is just a little short of that, right? Could be any of that, anything like that. Okay, so head loss then, if we track a similar trajectory here and cut off for backwashing and rinsing here, or excuse me, backwashing, air purge here, rinsing up front, maybe we have some head loss limit here. Well, as soon as we finish the backwashing, our head loss is actually going to be, it's going to be pretty easy to wash water through it. Even if particles are coming together and adjusting and the granules are finding nice spots, the head loss is actually just going to be pretty low at first, and it's going to be steadily climbing over time and eventually reach a point where we would have to stop operating. So pretty straightforward, pretty simple. There's no reason that we have a head loss limit during the rinsing stage is kind of the point there. Okay, so I want to give you some indication, some examples of what this would look like in practice. So you have a little more feel for it. I'll get to, I think I have plenty of time, so I might describe a little bit right here, and we'll probably end a little early. But let's take a look at a couple of videos. give you a feel for what this looks like in practice. Okay, and pardon me for just a moment while I make sure the sound is reasonable. We're not going to watch straight through all of this, by the way, because it gets a little tedious. But we'll watch a fair bit of it. I might adjust the lighting too. Okay. All right. So this first one includes an air purge, as we'll see. Actually, you know what? It's gonna... So you can see the air bubbles pumping up through there and making this nice, gross-looking slurry. Gotta have high-quality gross bubbles, right? Okay, so that process will really just go for about 5 minutes maybe, so we'll skip forward a bit. Oops, sorry. I don't know what. So it continues for a bit. And at this point, I'm going to mute it altogether because they're going to purge the pipes, and that's a very unpleasant noise. So they're getting all the air out of the pipes that they were just had in there to do the air flushing operation. And still going for a minute. Okay. So then they finished getting the air out. Now they're going to start pushing the water through, and you'll see all the residual air bubbles from the water start coming up. And one of these people, you can hear them make a funny comment.
Film the water for a bit. It's all bubbly. This is how they make root beer. Giant.
So in just a moment, the water will really start coming up because they're gonna push it up at about the same rate that they would normally feed it to it. And there's your delicious-looking root beer, right? So all that particulate matter was in the river or whatever it was feeding this this treatment, right? And this is after sedimentation has occurred, presumably. So it's catching a lot. Of course, this is many hours of operation, but it's quite a lot of junk there. And these troughs, by the way, this is a very common design. Is where it's feeding out right now is normally where you'd feed in, and then it fills this thing, fills these troughs, and flows the dirty water on top of the membranes, or not the membranes, the filters, to push through the filters and through. So in this case, it's literally reversing. And they're just going to change the pipes around a bit so that it's coming back out of them and back out the way the to-be treated water is normally coming in. So that'll go for some time, and then eventually we'd see it clear up. The next video I have shows the clearing of the water a little better. Okay. So we're definitely not going to watch full 18 minutes of this one. We can see these as similar design here with a trough in the middle and then these little kind of grates to let water flow through kind of evenly over and across them. So the backwashing is just beginning now. I don't think they did an air purge. I don't think they're planning to. And the water will just come out that trough. Actually, I could be wrong about the air purge. We'll see. You see that the color change, starting to see some orange. Okay, there we go. So now you can really start seeing its orange particles coming out as the water is being pushed up. Okay, so there is an air purge. So air purge will go on for a little bit of time. It stopped the air purge. And you can even see on the video, well, maybe you can't see it. On my screen, I can see it's been 6 minutes of video time so far. And this is where we're at, right? Okay, they finished the air purge at this point, and they're gonna just push the water through. That's probably the next 15 minutes of the video. Again, we're not gonna, we'll skip through, but you can see the particulate matter in this case looks a bit different. Now, it's a different color. That could be a different coagulant they're using, or that could be just a different geology of the area. Different types of mineral content, different types of clay particles. A lot of this stuff that we're seeing is probably some combination of the local sediment, clay, whatever particles that were in the water. And so it can certainly look a bit different. Some places will use ferric chloride as a coagulant. Some places will use aluminum sulfate, which is probably more like this color. So could be a function of what kind of coagulant's used. Okay, so then this will go on for some time, and it's pretty neat though. As it gets towards the end of the video, we'll see it clearing up a bit. Kind of a neat effect. So just skip forward about 2 or 3 minutes, and we can already start seeing patches where it almost looks like it's getting dirty in those patches, but that's actually probably where it's less turbid, because then we're seeing through the water a little further at these dark spots. Gradually improves. They stop and take a look at filter beds that are in operation over here, and what you notice is you don't even see the trough here because there's just water on top of the whole system. So there's enough water that it's pushed into there, and it's pushing its way down through the two beds, and it's coming into that trough and up, and then it's just forcing the only place water can go is through the beds. Is kind of how that's working. So cleaner and cleaner. Until you can pretty much see the sand or the media itself. And at that point, I think we just crossed that. So right here you can see, at this point I think they stopped the flow, the backflow, and they're going to start pushing water in. And so now it's or pretty soon they will start pushing water in. And at that point, they're going to start, you'll end up seeing all the particles sink back into the media because now the flow has reversed and it'll end up clearing it up nicely. And at this point, we're pretty much looking at like what it's going to look like. It'll settle a little bit and it'll start the rinsing phase of the operation. I think that's probably about it. Yeah. Okay, so let me, I'm going to say a couple more things real quick. Probably ought to have gotten the other slides ready, but we'll just let you off a little early today. Ultimately, what we want is some equation for the water efficiency for this. So we'll need water efficiency for the filters. And we're going to need to know something about not just the efficiency, but the actual amount produced. So we'll need water efficiency, some handle on the net water production, and having a net water production, this is going to be coming from some number of filters, their size, and the amount of time they can spend backwashing. So it'll account for that. It'll account for the time, let's see, in operation. So in one cycle, how much of that time are they producing water? How much of that time are they not doing anything? How much of that time are they consuming water that was already produced for the sake of backwashing and stuff? So there's several questions about that. And we just have to put all those pieces together to properly say, all right, well, to design something for these specifications that needs to produce X number of cubic meters per day, we need this number of filters, and so on. We will look at terms that include a loading rate for a filter. We'll call that VA. So we'll see loading rates. We will have a VB for a backwashing rate. And then we will also have an effective loading rate because the loading rate itself is during the filtration. Now, effectively, if we accommodate for the whole cycle where we're not necessarily producing water the whole time, that becomes an effective loading rate. So that's going to be, it's very rather simple math, but we will be dealing with a few things and it can get confusing if you don't have a handle on what we're talking about. Okay, so we will pick up there and explain all of that next time.